Morning. Welcome to Israel, to Jerusalem, to the Hebrew University. I would also like to welcome you to the Institute for Advanced Study, where we usually hold our school, but the Institute for Advanced Studies lecture hall is passing now innovations, and part of the price we pay is that we have to do the lectures here. It's about a 20-minute walk, so I hope it, at least from the point of view of the physical capabilities, it improves. I mean, I hope it won't rain bitterly, so you can make that work. I would, when I open, I'm the director also of the Institute for Advanced Studies, so when I open every school, I give also a general exposition about the Institute for Advanced Study, so it's a little peculiar for me to do it here among friends and students in physics in my profession, but I do it nevertheless. So the Institute for Advanced Studies is a national institute anchored at the Hebrew University, and it provides 3 levels of activities, and we are one of them. The main activity is research groups. We have research groups which stay for half a year or a full year, and they are composed of 8 people, 4 from abroad and 4 from Israel, not allowed more than 2 from the same university. So it's really an integrative effort. And we give this opportunity to any faculty for any place in the world. You don't have to be from the Hebrew University, you don't have to be from an institute in Israel. And actually we are having now in physics, in the subject of integrable systems, we are having from next semester a group which actually was proposed by people from outside Israel. There are some Israelis participating, but the initiative was taken from outside Israel. So this is really a great opportunity, and I encourage you to consider it from time to time. I think that in our group, maybe from Tel Aviv once, there was an initiative of Yakir Aharonov to have here a group. Usually the initiatives came from Jerusalem on this. Our second level of activity is conferences and workshops. They are again open to anybody from anywhere in the world. He can suggest a topic, and actually I think Ofer Aharoni from Weizmann, who I see here now, and Kobi Sonnenschein, which I don't know if from Tel Aviv University, which I don't know if arrived yet or not, actually also they've proposed a workshop which will start here in February, and I think it's actually it's an Israeli-Indian conference which we have instated a while ago. Then the third level of activity, and that is a level of activity which you are part of, are advanced schools. Their duration is about the duration of this school, and they are in 5 topics. We are very proud that in those topics in which Nobel Prizes are awarded, we have Nobel laureates as our directors, suggesting us the way, gently and less gently, suggesting us the way the school should go. And we are very fortunate to have David Gross, who is very dedicated to us and to the school, who is a physicist. We have in the life sciences, we have Roger Kornberg as director of the school, and in economy, we have Eric Muskin, a Nobel laureate from Harvard now, who is also a director of a school. In the subjects where Nobel Prizes are not awarded, we also have a school in Jewish studies, and we have a school in mathematics where Peter Sarnak from Princeton is the director. And this is one of those schools. Now, I want to express my deep gratitude to David, for we know how busy his life has become, and we really appreciate very much the dedication that he has shown to this and is showing towards the school towards the year. And without further ado, I give the stage to him.
I thought I would start the school by giving a special talk on that came out of a recent Solvay Conference that I chaired in Brussels in October, which was a very special occasion. And since most of you weren't there, Most of you weren't there. I thought you might enjoy the opening talk I gave at the Solvay Conference, which I'm blending together with some remarks on current trends, which is sort of the topic of this school, and say a few words of introduction or comments or personal views on where we stand at the frontiers of theoretical physics and the topics that will be covered by the lecturers. So, in October, at the Solvay Conference, we celebrated 100 years of these rather unusual meetings that are held in physics every 3 years in Brussels. The first of these was held 100 years ago in Brussels. This is the reprint of the book that Langevin and De Broglie put together from the presentations and discussions at the first Solvay Conference, where 24 physicists met at the Hotel Metropole in Brussels, invited by a Belgian industrialist called Ernst Solvay, who created at that time a new kind of scientific congress. This was one of the first international scientific meetings. At that time, you might find it hard to imagine today, where there's 3 conferences every week all over the world. At that time, there were essentially no international scientific conferences. Academic societies held their own meetings, but scientists from other countries didn't participate particularly. This was not only one of the first international scientific meetings, it was also very unusual in its structure, and still is. Very highly restricted list of invitees, and an unusual mixture of short talks and long discussions. The Solvay Conference has played a very unique and important role in the development of 20th century physics, as you all know, most notably in the quantum revolution, whose birth overlapped the initiation of these meetings. This tradition of holding these conferences in Brussels continued with a physics conference every 3 years, except for various wars that broke out in Europe in the 20th century, and is one of the few traditions that remains in our rapidly changing scientific landscape. A tradition of excellence and internationalism, free discussion, debate, a tradition worth preserving, but one that is rather hard to maintain in the context of the Solvay conferences of the past, since the number of physicists has increased by a factor of 100 over the century, whereas the number of people that one can invite to these very small, intimate meetings maybe has increased by a factor of 2 to 3. So for somebody that was organizing this conference, I'll tell you, it was an extremely difficult job that made many enemies. This is a famous picture from the Solvay Conference of 1911, which many of you, I'm sure, have seen. This was the total number of people who attended the conference. You see here Poincaré talking earnestly to Madame Curie while the photographer is trying to get everybody to be still. This is Lorentz, who was the chair of the conference at the time. And you might recognize other distinguished physicists. There is Rutherford. There's Einstein. Notice everyone had a mustache. It was a requirement, I think, of physicists at the time. Except for Madame Curie. This is Ernst Solvay, who actually attended the conference and presented. Ernst Solvay was a fascinating man. He had all sorts of very interesting ideas about how society should be run. For example, even though he was, the Bill Gates level of his time, he believed that there should be no inheritance. Everybody, all inheritance should be confiscated. His family didn't go along with that, and they still run the Solvay company, which is quite well off, and support the Solvay Institutes. But anyway, Ernst Solvay wasn't actually at this photography, so his head, which appears somewhat larger, is only larger because they pasted his head onto this picture. There's some controversy about Einstein here. Einstein here, you see, is, I think, about 33 years old, the youngest probably of the attendants. And you notice his hand looks kind of funny. Let's look more closely. There he is. And so there's controversy as to whether he was making the Buddhist sign of harmony or holding a little piece of a cigarette. Still open to interpretation. Next to him is Rutherford. So a young man at that time. Rutherford had just discovered the nucleus that same year, 1911. This was the birth of particle physics. This was the discovery that made it possible to explore not just the outer layers of the atom, atomic physics, but the innards of the atom, the nucleus, the strong, the weak forces that we spent the rest of the century since then understanding. And we have understood, more or less. This is also the birth of elementary particle physics because this was the first use, the beginning of the method, the experimental technique we've used for the last 100 years to explore the properties of particles and forces. Namely, you take two particles and you smash them together and you look at what comes out and you try to figure out what went on. That's what Rutherford students, Geiger and Marsden, did, 1911, by smashing alpha particles, helium nuclei off gold, and measuring how they scatter. And Rutherford, 1911, had 6 months before this meeting published a paper in which he proved, based on those experiments, that in the center of atoms there's this very small nucleus which looked to him like a point. He could only put lower bounds on the size of the nucleus. So it was very small, he knew that, and that's where all the charge and mass was located. Interestingly, at the Solvay Conference, he didn't say a word about this discovery. His older and much more famous at the time colleague, J.J. Thomson from Cambridge, talked about his model of the atom, which consisted of sort of diffuse stuff with electrons embedded. It was called the plum pudding model. Rutherford made one remark in the discussion saying that, well, there's, pointing out some problem with this model, but he never talked about his unbelievably important discovery, strangely enough. It could be, although I've been trying to ask historians of science to explain this because his French wasn't very good, and the conference at that time was held in French. Okay. So for the centenary year and for the 25th Solvay Conference in Physics, we decided to cover physics very broadly, but to focus on quantum mechanics, whose early birth pangs and later applications were the subjects of these Solvay meetings over the years. Quantum mechanics is roughly 100 years old as well. Hard as that is to sometimes believe, it's only 100 years. It emerged, perhaps the beginnings of quantum mechanics, as you all know, began around 1900 when Planck first quantized the energy of radiating oscillators and came up with his black body radiation law, which worked beautifully. So everybody at that time began to think that the quantum of action and quantum was real. But that quest to understand Planck's formula, Planck's derivation, quanta, didn't really end until 1925-26 with Heisenberg, Schrödinger, Born, and Dirac's formulation of the principles of quantum mechanics. And 1911 was the beginning of the first Solvay Conference, which was devoted to the theory of radiation and quanta. And the subsequent 5 Solvay Conferences were all devoted to the emerging structure of quantum mechanics, the structure of matter, 1913, atoms and electrons in 1921. You see the war stopped things. The electric conductivity of metals and the first applications of quantum mechanics to materials, and electrons and photons, 1927, which is perhaps the most famous of the Solvay conferences. Here's a picture from that conference. You see now Einstein at the center, a little older. There's Lorentz, who died 6 months after this picture was taken, Madame Curie, but also Bohr, and Heisenberg, and Pauli, and Schrödinger, and Dirac. This famous conference, the the meaning of quantum reality was heatedly and famously debated between Bohr and Einstein, and the young pioneers who had developed the quantum mechanics almost as it stands today discussed its structure. Back to the first Solvay conference, 1911. It addressed the central problem of physics at that time. Was the quantum structure of nature truly unavoidable? Lorentz's opening address at this first conference reverberates with the anguish and pain that this master of classical physics felt at the first glimpses of this new quantum world. And to quote Lorentz, he said, "Modern research has encountered more and more serious difficulties when attempting to represent the movement of smaller particles of matter and the connection between these particles and the phenomena that occur in the ether." Parentheses. It's really, I found this amazing that 1911, this is 6 years after Einstein's theory of relativity, Lorentz, a very intelligent, smart, great physicist, couldn't rid himself of this concept of the ether. Close parentheses. At the moment, he says, we are far from being completely satisfied that with the kinetic theory of gases, gradually expanded to fluids and electron systems, physicists could give an answer in 10 or 20 years. Instead, we feel now that we have reached an impasse. The old theories have been shown to be powerless to pierce the darkness surrounding us on all sides. So that was his feeling, and the conference devoted itself to this question. There were people, Planck gave a talk on his theory of black body radiation. Einstein contributed quite a bit to the discussion. People were very unhappy Well, we face no such crisis today. Quantum mechanics works. It makes sense. And it is really hard to modify. It is the most successful of all frameworks that we've ever discovered to describe physical reality, together with the theory of relativity. It works, it makes sense, and it is hard to modify. Oops. This list, by the way, these are the three things that matter to physicists. First of all, that it works. Then that it makes sense as well. And then we try to modify things and, you know, construct something better or different, or we're forced to do that. Well, in the case of quantum mechanics, it works extraordinarily well. We now know that it makes sense, and it is really hard to modify. So let me start with the second point, that quantum mechanics makes sense. The transition 100 years ago from classical to quantum reality was extremely difficult and painful. It took a long time to get out of phase space and to locate oneself and understand Hilbert space. Some of the boldest pioneers, notably Einstein, resisted the replacement of classical determinism with a theory that most often can only make probabilistic predictions. Even harder to get used to was the idea that in quantum mechanics, one can describe a system in many incompatible ways, and there is no unique, exhaustive description. The freedom that one has to choose between different incompatible frameworks does not influence reality. One gets the same answers for the same questions no matter what framework one uses. That's why we are allowed to do what most physicists do, shut up and calculate. Most of us do that most of the time. But different incompatible aspects cannot both enter a single description. And if one errs by mixing incompatible descriptions or histories, you get into paradoxes very quickly. And even today, many people still get quite confused about quantum mechanics, and for that reason think that it should be replaced by something else. But in my opinion, by now, especially with what is called the consistent histories approach or decoherent histories approach, we have a completely incoherent formulation of quantum mechanics that actually corresponds to what we do when we observe, measure, and calculate. Although there are still people who believe that quantum mechanics needs to be altered. And at the Solvay Conference we had 2 months ago, there were such proposals. And more important for physics, quantum mechanics works. And it works not just for simple systems like atoms and molecules for which it was originally developed. Not just for explaining the structure of atoms and molecules, thereby chemistry, but collections of 10 to the 23 atoms, often strongly interacting over an enormous range of energies and conditions. It explains not just the anomalies in the classical description of black body radiation and the specific heat of solids at low temperatures that stimulated early developments, but also the detailed properties of ordinary matter, conductors, insulators, semiconductors, superconductors, and more exotic materials. The quantum theory of matter, many-body theory, and the quantum theory of fields, which was developed almost immediately after the quantum mechanics was founded, share many common features. In fact, they're essentially the same thing. And as you all know, critical developments in condensed matter physics and quantum field theory and particle physics towards the end of the 20th century shared many common features: spontaneous symmetry breaking, renormalization, group transformations, etc. And once they started talking to each other, these fields benefited immensely from cross-fertilization. Quantum mechanics works. It describes, among the rest, one of the most important quantum phenomena, that of dynamical symmetry breaking. And one of the most important examples of symmetry breaking, superconductivity, the fact that certain metals conduct electricity without resistance at low enough temperatures, was discovered also in 1911, in the same year, by Olnes, who won the Nobel Prize for that discovery 2 years later. Unlike Rutherford, Olnes did describe his discovery at the first Solvay Conference. And superconductivity, as you know, was the first example of the spontaneous breaking of a local symmetry, which later played a fundamental role in the understanding of the nuclear force, the so-called Higgs mechanism, the final confirmation of which we are anxiously awaiting from the LHC, and we'll hear about during this conference. Interesting, it took 46 years, until that phenomena was understood. I just read recently a recently translated paper by Einstein on a theory of superconductivity. Every physicist worth his name tried to understand superconductivity for over 40 years without success. So don't get discouraged if we don't understand, can't calculate the cosmological constant yet. Sometimes takes time. BCS, who understood and derived qualitatively and had a quantitative model of superconductivity, which still is good for most superconductors, essentially laid down the essence of what played a big role in the development of particle physics, the spontaneous symmetry breaking of the electroweak gauge symmetry. So superconductivity really had a very important role, and again is 100 years old this year. Even today, unconventional superconductors, so-called high-temperature superconductors that were discovered over 25 years ago, are still a great mystery and provide great stimulus towards the frontiers of condensed matter physics and the understanding of exotic materials, heavy electrons, spin liquids, graphene, topological insulators, emergent gauge theories, non-Fermi liquid theories, quantum critical points. All these are topics in many-body quantum theory that were heavily discussed at this year's Solvay Conference and continue this century-old tradition. Quantum mechanics really works, but there's still many quantum mysteries left even in the understanding of ordinary matter. What are the possible kinds of matter and materials that exist or could be designed, or could be understood, controlled. And of course, this is the frontier of modern technology. It works. Quantum mechanics works using the combination of relativity and quantum mechanics, quantum field theory, at distances that now extend 1 billion times smaller than the size of the atom, well within the nucleus and its constituent quarks. It works and has been verified experimentally for energies that are 1 trillion times higher than the atomic energies for which it was developed. From the beginning, shortly after its birth, it was clear that quantum mechanics fits together seamlessly with special relativity and Maxwell's theory of the electromagnetic field, with some technical difficulties that took some time to resolve. The quantum theory of fields that permeate space and transmit forces resolved the perplexing duality of particles and fields, particles and waves. And in what I regard as one of the most amazing successes of theoretical physics, predicted the existence of antimatter before it was seen experimentally. But the first examples of which, the anti-electron, the positron, were soon discovered. And quantum field theory is tested with extraordinary precision. Much of the incredible precision of fundamental physics rests, in fact, on certain features of quantum mechanics that are absent in the classical framework, such as the identity of indistinguishable particles and the existence of discrete, sharp energy levels and frequencies. I can't refrain from showing one of the examples, the anomalous magnetic moment of the electron, sort of the magnetism of the electron is measured to 1 part in 10 to the 12. This is unbelievable experimental accuracy. 12 digits. And the theoretical calculation of this number has been done to equal accuracy, and the discrepancy, which is well within the error bars, is 1 part in 10 to the minus 12. The range of quantum field theory, relativistic quantum mechanics, as far as we can tell, extends from the edge of the universe, which is about, at the moment, 10 to the 27 centimeters across, to a nano centimeter, 10 to the minus 18 centimeters. That is experimentally verified. And we have no reason to suspect that this framework breaks down till we get to distances of order 10 to the minus 13 centimeters, 33 centimeters. So relativistic quantum mechanics is, as I said at the beginning, the most extraordinary physical theory we've ever had, with this incredible range of validity, precision, and range of applicability. It provides not only the explanation of the structure of atoms and molecules, but the structure of the nucleus as well. The strong and, the strong and weak nuclear forces that govern the nucleus. In a reductionist sense, the standard model of elementary particles, which is summarized here with the various families of quarks and leptons and the various forces that act within the atom, is an amazing framework. It's flexible enough to encompass almost all the known forces that act on the known particles of nature, with the exception of dark matter and the right-handed partner of the neutrino. And it is so extraordinarily successful that we currently strain and have been frustrated for the last 3 decades to find any deviation from it. And yet we know, of course, that there has to be physics for various observational and theoretical reasons beyond the Standard Model. We have the experimental discovery by astronomers of the fact that most of the matter in the universe consists of some, most likely, very heavy particle that we have never directly detected, except by seeing that it pulls stars around the centers of galaxies. We have the fact that neutrinos are not massless, but are massive. That can be understood, of course, easily by modifying slightly the Standard Model, but it goes beyond it in ways which we're not sure of yet. We still don't understand why the universe is full of baryons and with very few antibaryons. And astronomers have also, this year's Nobel Prize was awarded for the discovery of the accelerated expansion of the universe, which it seems is due most likely to energy pervading the vacuum, whose magnitude poses an enormous theoretical mystery. From a theoretical point, our understanding so far cries out for unification. All of the particles we have that make up the matter we observe and measure, and the forces look very much like they come from a common origin. The different symmetries that lead to the 3 forces that act within the atom fit together like pieces of a jigsaw puzzle, except we're not exactly sure what the total puzzle looks like. We have problems, theoretical problems, with the so-called naturalness of the Standard Model. We have the scale of the electroweak, W and Z boson masses, compared to the unification scale, or the scale of gravity, where gravity becomes strong. The hierarchy, we have the masses of the elementary particles, which we can't explain, their mixings, the existence of 3 families. We have hints from cosmology of new kinds of dynamics that must be there to give a fundamental explanation of the initial inflation of the universe. And then, of course, the vacuum energy is a severe theoretical problem. In our hopes to understand these problems, experimental and theoretical, we're going to have to go beyond the Standard Model and search for a source. Search for... and three of these problems, the unification of the forces, the hierarchy of the electroweak scale, the big disparity of those scales, and the existence of dark matter, are 3 clues that a new and profound symmetry of space and time might be present, so-called supersymmetry, which in effect is enlarging our vision of space-time to include quantum dimensions and the symmetries of rotations in this new, larger quantum space-time. And supersymmetry, which is really beautiful and predictive and addresses those three issues, has been the focus of the experimental, well, theoretical for many decades, and now experimental searches for understanding. From the point of view of theoretical physics, enormously appealing because of its beauty, its connection to string theory, but more importantly, it addresses those three fundamental problems of beyond the standard model physics. The problem is that although the symmetry is beautiful and predictive, supersymmetric models that must incorporate the obvious fact that that symmetry is not manifest, broken, and we don't have a theoretical understanding of how that occurs. We have many ways of implementing that. Supersymmetric models are not particularly beautiful or predictive yet. We're going to hear a lot about that from Michael Dine, who will start today talking about supersymmetry from the bottom up or the top down and bring us up to date. The LHC's most exciting goal in Geneva, the Large Hadron Collider, is to discover supersymmetry, is to discover these quantum dimensions of space and time. So far, they haven't seen any signal, which tells us that the most optimistic hope of some that colored, strongly interacting supersymmetric particles are around the corner is wrong. They're not around the corner. But there are a lot of things around the next corner that we still await. The other thing, as you all know, we're expecting from CERN is the discovery of the Higgs particle, much in the news lately. So about a month ago, I was contacted by a reporter from the Nature magazine who said, I'm writing an article on the Higgs particle before the press conference next week. What do you think? Do you believe that the Large Hadron Collider is going to discover the Higgs particle? So I made the mistake of answering and of starting out my email message by saying, absolutely. And then I explained in 2 paragraphs a very carefully thought out answer to this question. And of course, the only word he took from me was absolutely. So here he plotted, this is degree of belief of all sorts of people like Tom Kibble, who's one of the contenders for the Nobel Prize for the Higgs particle if they ever discover it. And he said, in some ways, I would prefer that it is not found, which is really a personal statement, not a physics prediction. Then there's Steve Weinberg, the founding director of the Jerusalem Winter School, who's wearing a SSC, I think, construction hat. And he's saying, there are other possibilities. That's really hedging his bets. Then there was Shelley Glashow, who made the statement, see, these people are much more experienced than I am. They know how to word these things. He said, if not in 2 years, then never. Well, that's true, but it didn't answer the question. Then there was Lisa Randall, who said, so she's almost yes, hopefully. Then there was John Ellis, who said, as a fully paid up supersymmetrist, I have to say yes, which is also a strange answer. Then Frank Wilczek, these are yes. I remain optimistic. And I unfortunately said absolutely. So anyway, I was very happy when last week or 2 weeks ago, how old is it now? 2 weeks? Atlas announced at a seminar at CERN a 3.6 sigma signal for a Higgs around 124 to 6 GeV. This is the error. Now, for those who are not physicists audience, physicists now are extremely conservative, right? They demand for discovery of something what we call 5 sigma, 5 standard deviations, which means roughly that the probability at that level, if you believe mathematics, of the discovery being false, being an accident, is 1 in something like 30 million. That qualifies as a discovery. Now, if you take this number, 3.6 sigma, seriously, there's a 1 in 3,000, something like that, chance that it be false. That's too dangerous to make a conclusion based on the chance that 1 in 3,000 you're wrong. So physicists become very conservative. Now, so Atlas did not claim a discovery. And in fact, they said, there's a nice bump here which sticks out, but that could have occurred anywhere. And if you take that into account, the significance is reduced to 2.3. Anyway, I was quite impressed by that. If you combine this with, on the web, unofficial combination of all the experiments, CMS and Atlas, and the LEP, bounds, and Tevatron, you get a 4 sigma effect. Looks pretty good to me, so I think the Higgs probably has been discovered there. And we're going to hear about that during this school, and about the other incredible measurements that have been made at the LHC by Atlas and CMS. Among the rest, subjecting the standard model to unbelievable tests of precision. I mean, I enjoy, this is a test of QCD over 6 orders of magnitude of the dijet cross-section. And of course, it's this understanding of the standard model, both and that allows us to search for these small signals. But it is quite impressive what the LHC is going to contribute to our deeper testing and understanding of the standard model as well. So we're going to hear 2 contributions on LHC results, one from Maria Spiropoulou from CMS, and one from another Gross from Atlas, who will report specifically on the Higgs particle searches. So coming back to quantum mechanics and our general theoretical framework. One of the remarkable things about quantum mechanics is that it is so hard to modify. Our present fundamental framework, quantum field theory, is under no threat. It's very different than 100 years ago. There are no threats. There are problems, things you'd like to understand better, calculate better. But there's no threat from observation or experiment as there was 100 years ago. Quantum field theory seems completely adequate for the understanding of macroscopic and microscopic physics from the edge of the universe to the nanometer scale. It's even difficult to construct alternatives to this framework that agree with observation. A lot of people have tried. Construct something that is not quantum mechanics. Let's say an underlying deterministic theory, or something that replaces the Schrödinger equation, which is a linear equation, with something which is slightly nonlinear. As soon as you try to do anything like that, and if you have never tried, take a day off sometime and try. Things immediately explode and go wrong in every possible direction. However, we all know from the history of physics that no framework, no theory is likely to survive untouched forever. So an interesting question is, where might our present quantum mechanical framework break down, and how? Now, most of the attempts that people have tried over the century to modify quantum mechanics are pretty ugly and unmotivated, which is probably why they failed, one of the reasons. All hints we have from thought experiments and trying to extend our understanding to new regimes, new questions, are the only way we really can proceed at this point. One problem that stares us in the face, so far we don't understand, is the unification of the forces. It's clear from the pattern that we observe that the forces of nature are unified, probably at very high energies. The other hint we have is from our lack of understanding of the quantum nature of space and time, cosmology, general relativity at very short distances. And a third hint is just from the true understanding of quantum field theory, which I thought I understood pretty well 25 years ago. But it is a moving feast. It is a changing story. And we are learning more and more about quantum field theory itself over the years as we try to address some of these other issues motivated by unification and by gravity. And we're going to hear about some developments purely in old-fashioned quantum field theory from Zohar Komogodsky from the Weizmann Institute, who will talk about very recent developments in understanding renormalization group flow in quantum field theory. Now, quantum field theory in its traditional sense is not sufficient to contain gravity. Or the usual approaches to quantum field theory were not sufficient to contain gravity and led us, in our attempt to unify, to string theory, which is now in its 43rd year of development. And I think that is way older than most of the people in this audience. String theory, which began with an attempt to understand the open strings that exist when you pull quark and antiquarks apart, we now understand as flux tubes in QCD, led to although that was the original motivation for string theory, as a theory of strongly interacting flux tubes and the strong interactions, the realization that open strings necessarily can be closed to form closed strings, which contain the gravitational sector of the dynamics, led to string theories as candidate unified theories of all the forces, and were truly viewed as the first and most exciting and different attempt to go beyond quantum field theory. A revolutionary new development that would lead to a theory of everything. That's how it appeared 25 years ago. One of the major developments in the last decade and a half has been the realization of a profound, this duality, if you want, between open strings and closed strings, different ways of looking, is profoundly built into the structure of string theory and quantum field theory. Of course, that's the ITP, KITP in the background. The most profound example of which that has been the subject of intense research for the last decade and more has been the correspondence between a string theory in anti-de Sitter space and conformal field theory in ordinary space without gravity. The realization originally that solitons, or extended objects in closed string theory, brains, can, low energy dynamics is that of gauge theories. They are the source for curving the geometry of 10-dimensional space. And there's a profound duality between, and the best example that we have between closed string theory, 2B string theory in a ADS times S5 background geometry, and for ordinary gauge theory, supersymmetric Yang-Mills theory with maximal supersymmetry in 4 dimensions with no gravity. This duality, so-called, between a field theory of the normal type, the one uses in the standard model, and closed string theory in particular background has modified what I regard now as the existing framework for theoretical physics. Quantum field theory and string theory are not really different. What we've learned is that quantum field theory is much more interesting than the simple quantum field theories than our understanding of it was 25 years ago. And that string theory, which we never completely and still don't understand, is not that different from quantum field theory. The two are really the same. This is, in fact, I think many of my colleagues would agree that most likely any consistent quantum field theory, which, remember, in our modern way of looking at things is we understand by understanding the conformal field theory to which it flows in the infrared or the ultraviolet, is dual to some, or equivalently described by some string theory, perhaps in a very curved and strongly interacting background. I don't think anybody would truly have a good way of disagreeing with that statement, although it is much stronger than what we could actually show. So string theory has turned out not to be a revolution. Once again, quantum mechanics or quantum field theory, quantum mechanics plus relativity is extremely hard to modify. We've just learned that quantum field theory is much richer than we previously understood. And so I tell I tortured Shelley Glashow a few weeks ago by telling him, you can't kill string theory anymore. It's impossible. It's a standard model of string theory. On the other hand, that's a bit depressing from the point of view of the desire of every red-blooded theoretical physicist to participate in the next revolution in the framework of theoretical physics. There probably will be revolutions, there always are, but they haven't come yet. And that's one of the problems. And before I say a word about those problems, let me remark about how we have been exploiting this incredible correspondence to understand much more deeply quantum field theory or string theory. And the way I like to put it is that we have found the hydrogen atom of quantum field theory. What I mean by the hydrogen atom is a system that is simple enough so that you can solve it exactly on a few lines, an integrable model that has extra symmetries that are powerful enough to completely solve the theory, but it's a good approximation to the real world. And such models, like the hydrogen atom, have played a fundamental role in the history of physics, if you think about it. Especially the problem of the two-body interaction, a system that contains just two bodies, or one if you remove the center of mass, with an inverse square law force. That gave rise, the existence of such a simple system, like the Earth going around the sun or the moon around the Earth, gave rise to classical mechanics. It really would have been hard to see how Newton would have developed the laws of classical mechanics if he didn't have this simple integrable system to work with. If he had some chaotic dynamical system, it would have taken at least another 20 years or 200 years. The Bohr model was based, in fact, the success of this first model of the atom, almost 100 years ago now, was based on the fact that the hydrogen atom is an integrable system in quantum mechanics. So Bohr was able to write down semi-classical approximation to a theory he didn't have yet, which was exact because of this integrability. And, it's hard to see without a simple integrable model how quantum mechanics would have developed so rapidly. Non-relative, that was true, actually, still integrable when quantum mechanics was discovered. It was true for the Dirac equation of the hydrogen atom, whose, again, precision, you could calculate exactly, and discrepancies with that led to relativistic quantum mechanics and quantum electrodynamics. Well, we haven't had in the study of the nuclear forces or physics beyond non-relativistic quantum mechanics many nice examples of integrable systems. A lot of two-dimensional field theories which informed us about the structure of quantum field theory, renormalization group, et cetera, et cetera. But not many examples in 4 dimensions until now, and now QCD, of course, became closer and closer to an integrable model at very large momenta, and that's extremely important because it gives us the ability to calculate, for example, LHC backgrounds. So at least we have an integrable, trivial, free field theory, almost. But that's the only example until recently where n equals 4 supersymmetric gauge theories, just the gauge theories we use in the standard model, but maximally supersymmetric and in the limit of infinite colors, is, it appears, integrable and completely soluble and almost solved. And it is a good approximation to the real world. To actually make contact with the real world, we have to break supersymmetry, put in quarks, expand in 1 over n, and that'll take some time. Not only that, it is dual to a string theory in 10 dimensions. So this, I believe, and the reason so much of research in string theory and quantum field theory has focused on this duality and on this theory is that it can play the role, has been playing the role of the Earth-Moon system or the Bohr or the hydrogen atom. It's not only beautiful, this connection, this model, but useful. It forms the basis, starting point for calculating important, phenomenologically important amplitudes, QCD scattering amplitudes. It informs us about the quark-gluon liquid, using the correspondence with string theory, and now many-body theory, condensed matter physics, ADS-CMT. It's not only useful, but important, because it connects to many of the deepest issues we encounter in our attempts to understand quantum gravity. Black holes, the Big Bang, emergent space, all of these deep issues on the gravitational side of physics, we can approach now using this, starting from this integrable quantum field theory. And it informs us as we try to understand the connection between the ways of looking at string field theory about field theory and string theory. And many of the lectures in the school this year have to do with probing these kind of dualities, these kind of almost or fully integrable models. Starting with Zvi, who will talk about calculating scattering amplitudes from QCD to gravity. Nikita will talk about integrability and the geometry of slightly less supersymmetric but richer, more complicated four-dimensional gauge theories. And Nima, who will talk about, well, I bet he will talk about space and time and n=4 supersymmetric Yang-Mills theory. So this takes us to this, still to this question, we don't know what string field theory is. String theory is not really a theory, because field theory isn't really a theory either, it's a framework. To make a theory like QCD, you say, okay, there are 3 quarks, there are 3 colors, and there are so many families, and they have masses, and that's a theory. You have to put in extra stuff. And so one of the main issues of fundamental physics is what's missing in string theory. What turns string theory into a theory? Now, there are people who say nothing's missing. Everything that's allowed in the framework is there somewhere in a multiverse of worlds. But perhaps we're actually missing something fundamental, some new principle that produces a theory and not in this framework, or changes the framework in some revolutionary way. So there are really 2 questions. What fixes the dynamics? What picks out a solution? It's one way of doing it. Or what principle fixes the dynamics? What turns this framework into a theory? And you know you have a theory when you can disprove it experimentally. And as I explained to Glashow, string theory can't be disproved at the moment. And what fixes the initial and final state of the universe? Because if we've learned anything from this, well, we now know that string field theory contains gravity as in the ultraviolet. And once you have a theory of gravity, you have a theory of space-time, dynamical space-time. And once you have a theory of dynamical space-time, you have to ask the question, what fixes the initial state? Now, of course, we also have hints that space and time are a bit suspicious. Most of our notions of space and time, classical notions, like a smooth manifold with a fixed number of dimensions, with a given topology, no longer make any sense in string theory, where all of these things can be changed and violated and superseded. And we have well understood by now examples where, in one way of looking at it, space-time is emergent, such as ADS-CFT, where the scaling dimension of ordinary quantum field theory emerges as an extra dimension of space. And other examples where all of space emerges as a description of phenomena at large distances. Is space-time really an emergent concept? Should we be looking for a framework in which space and time emerge and are not fundamental? Well, time, can we imagine physics where time is emergent? There might be more than one dimension of time. And what are the rules of physics if you don't start with space and time? Personally, I suspect that this direction, that these questions are crude forms of profound questions that we will have to answer. And one talk in this school will be devoted to such ideas. Eric Verlinde will talk about attempts to understand how space and time emerge, and gravity and other things from something we'll hear. But more generally, even if space and time aren't totally to be thought of as emergent quantities, we just don't know what the rules of quantum cosmology, of the dynamics of space and time are. And in my opinion, we haven't come to grips with the fact that the goal of elementary particle physics has changed. It used to be, the goal was to find the vacuum, to find what the vacuum looks like, and then do little scattering experiments where you slightly perturb the vacuum and measure probabilities for scattering of these little particles. But in quantum cosmology, if space and time are dynamical, then the answer is the universe, the whole space-time manifold, not just a static, stationary state, which if you didn't do anything would not change as time evolves. But the whole space-time history, that's the answer to the question that physics poses. And if you have to understand space-time history, that includes the beginning, the boundary, the end, everything. It doesn't really make sense, it seems to me, just to describe what happens in a period of plus or minus 1 billion years around today in a restricted region of the universe. The solution has to describe, and we don't know what the rules are. We don't even know what the observables are. In some cases, there are no observables at all. We're on very shaky grounds in trying to understand quantum cosmology. We're going to have 2 talks. Slava is going to keep us, Slava is going to keep us honest by Slava is going to keep us honest by talking about what we can actually observe cosmologically in our universe, and what we might hope to observe, and what the fundamental issues are. And Eliezer is going to talk about attempts within string theory to deal with some of the singularities that classical reasoning, that standard reasoning tends to produce, which we still don't know how to resolve. And finally, we have the problem, the greatest theoretical challenge to us is this measured now vacuum energy. The cosmic expansion, this year's Nobel Prize, was for presumably measuring the cosmological constant, the vacuum energy. Now, in a sense, except for the fact that theorists were so silly or stupid for the last 50, 100 years, this is a great triumph of general relativity. Einstein once famously said that the cosmological constant was the biggest blunder of his career. Remember, he realized that a volume term in the action is just as natural as a curvature term. So his theory contains the possibility of a vacuum energy, we would now say. And he actually used it to construct a universe that was static, a universe that was unstable also. And he soon abandoned as the observations revealed that the universe was expanding. And so a lot of people think that what he meant by the biggest blunder was trying to introducing the cosmological constant. But I think what he really meant was his biggest blunder was not predicting the expansion. He could have predicted the expansion. Some Friedman and others, Robertson discovered the solution of Einstein's equations, and he could have done that. That was his biggest blunder. But he did introduce this term in his equations, and that led to a prediction which he knew couldn't be verified in his lifetime, that there were just bounds, but that cosmic acceleration that was discovered, the great vindication of general relativity, because the form of dark energy and negative dark pressure that it predicts precisely agrees with observation. It's a form of vacuum energy without an ether, without a preferred observer. The only possible form. So this is, in a sense, a great triumph of theoretical physics and explains observation. Then there's a theoretical problem that we don't understand the magnitude of this number by, some people say, 120 orders of magnitude, which has led some of my colleagues to say, okay, big deal, we simply have 10 to the 500 universes, and only a few of them have a small cosmological constant, so no surprise that we measure it to be so small. Otherwise, we wouldn't be here to ask the question. Luckily, there are no lectures. Maybe. What? Accidental. So I'm just going to end with my pitch, which many of you have heard before, of whether we could possibly explain this cosmological constant. If supersymmetry were exact, then we would have solved the world. And in fact, most of the multiverse is filled with exactly soluble, supersymmetric string theories in flat 10-dimensional space, which have no problems, strong coupling. Ofer is shaking your head. You disagree? Why?
I don't see why you think that's most of it.
Well, because they have continuous moduli. They're an infinite number. So infinity is bigger than 10 to the 500 or 10 to the 600.
Yeah, empty spaces, sure.
Well, no, how do you count? Anyway. No, a modulus, if it's fixed at 10 to the 500 discrete values, gives me less universes than a modulus that can take any continuous values. Anyway, if you break supersymmetry, there's another scale, so I actually try to make this number a little easier to calculate by relating it to the SUSY scale and then taking the fourth root of this energy density to get a ratio of mass scales. Still, 10 to the minus 16 is a very small number. Now, I remind you that Dirac, 1937, was the first person I know to, as the first physicist to take note that the universe is filled with large or small numbers like that, like, for example, the ratio of the proton mass to the Planck mass, 10 to the minus 19. Dirac wrote this beautiful paper in 1937 pointing out that there were 5 or 6 such very large numbers, and he formed these ratios of these numbers, the size of the universe compared to the size of the atom, the proton mass to the Planck mass, etc. And he noted, well, all these numbers are similar. They're all sort of like 10 to the minus 20 or 10 to the 20. Or 10 to the 20 to the fourth power or so on. And, you know, well, Dirac was a smart guy. One thing he didn't do in this paper was invoke anthropic arguments, which he could have. The anthropic arguments were around since the 19th century. He knew about them. He could have said, well, the reason the proton mass is so small compared to the Planck mass is that there are a multiverse of universes. In most of them, it's of order 1. If it's of order 1, all of you would be black holes. You wouldn't be here to ask the question. So we don't live in such a universe. The only way we can get big things, big stars, planets, people, is if this number is very small. This is a much easier anthropic argument than the ones that people like Weinberg use for galaxy formation. Dirac did not stoop to that level. He did make a theory, though. He was a physicist, so he said, I can't calculate all these numbers like the radius of the universe, radius of the atom, but maybe they're all proportional if you take the right power. And that led to a prediction. So the size of the atom is governed by the fine structure constant. Size of the universe changes. Right? The universe is expanding. So the size of the atom has to expand as well if this ratio was fixed. So he predicted that alpha and Newton's constant, some other arguments, would change cosmologically over cosmological time. This was disproved experimentally by looking at spectral lines on faraway galaxies that take billions of years to get to us, or by studying a natural nuclear reactor in Africa, which is very sensitive to the fine structure constant over the billion years. So anyway, he made a prediction, which is great, and it was ruled out. So but his origin is one of his big numbers, small numbers, was solved by QCD. We understand that 10 to the minus 19 to logarithmic accuracy because of a physical phenomena, the logarithmic running of the coupling. So the size of the nucleus is determined by the distance where the strong interaction becomes strong, which is related to a unification scale where the coupling, the Planck scale, where the coupling is, small, normal size. We don't know exactly where this is, what this is, but it doesn't matter because of the logarithmic running. The logarithmic physical running of the couplings. So the reason the proton mass is so weak, is so small, is that it's e to the minus 1 over the coupling. We can't calculate exactly, but this is the qualitative explanation, clearly. We understand it's not a problem anymore. It's a great challenge to unified theory to calculate this precisely. And we understand the same, we think, of the hierarchy of the electroweak scale, W and Z meson masses, to the gut scale. In fact, reducing that problem to logarithms in the same way is one of the motivations for supersymmetry, which, if we discover, we'll understand qualitatively that very small number as well. The third small number we understand is neutrino masses, which might be due to a different mechanism, the seesaw mechanism. But again, we can understand these, presumably, we think, perhaps, this very small ratio of neutrino masses to the top quark mass or whatever. There are three very small scales in fundamental physics, which none of us worry about. Certainly the proton mass, we understand. These two, presumably, is not a subject of deep concern. It is a strong motivation for supersymmetry or for the seesaw mechanism for another. But, doesn't force us to invent multiverses. So I don't see what the problem with the cosmological constant is, truthfully. The problem is not that it's so small, it's just that we don't understand how to calculate it. But not understanding how to calculate something doesn't mean that there is no answer. It just means that we don't know the answer. And that poses a great problem for theory, of which there will be no explanations in the talks in this school. Okay. So that's my talk. Thank you.
Any questions? Any counter strategies?
You claim that quantum mechanics makes sense, and you concluded from a coherence and coherence of quantum mechanics. So what does it imply on the way that we understand quantum mechanics? So should we all adopt now a many-world interpretation or other interpretation? Or?
No, we don't. You don't need a many-world. As I said, most of the time you don't need to worry about interpretation. Shut up and calculate is good advice. If you want to understand how to describe reality, I think that, as I remarked, our understanding of that has improved greatly over the years. Partly due to very carefully thought out ways of saying better than they did the interpretation of the originators of quantum mechanics. I mean, essentially, Bohr and Heisenberg understood quantum mechanics and explained it very well. And nothing they said is wrong. But they were living through a period where, of change. It was extremely difficult to undergo that, and they didn't always express themselves so well. So certain terms like collapse of the wave function, which make no sense, have found their way into some of the lesser text in quantum mechanics and have made it difficult to understand for many people quantum mechanics as they learn it. There are much better descriptions of the basis, the interpretations of quantum mechanics nowadays, which don't really differ too much from the Copenhagen interpretation, but get rid of a lot of the garbage. There's also there's a growing understanding of the physical phenomena of decoherence, which has now become a practical issue in experimental physics. You know, of constructing quantum states, protecting them from the decohering effects of the environment for the purpose of doing quantum computation or other quantum preserving other quantum effects. So the understanding of quantum mechanics truly has deepened. If you're interested, I would commend to you Robert Griffiths, who was one of the pioneers of that effort. His book on consistent quantum, I think it's called Consistent Quantum Mechanics, or Consistent History's Approach to Quantum Mechanics. There's an absolutely beautiful exposition of how to view and understand quantum mechanics, resolve all the so-called paradoxes that bother every student of quantum mechanics, the Schrödinger's cat paradox, and all of them in a way that is clearly matches what we actually do in the laboratory and in making predictions. So on the other hand, there still are many people who continue to question the foundations, interpretation, or the need to replace quantum mechanics with something else. And so far, they've had no success, experimentally, observationally, or even come up, as I said, with a consistent alternative.
Yes, you reminded us that string theory and quantum field theory are really the same thing, deep down. But there is one thing that is puzzling, and I'd like to hear what you think. String theory is a quantum theory of gravity. So quantum gravity appears naturally in string theory. There is no real issue with quantum theory of gravity in string theory. It's been a long-standing problem. So how do you reconcile this problem with the fact that string theory and quantum field theory are the same?
Well, so first of all, you said that quantum field theory, unless you put it in, doesn't contain quantum gravity. Well, we've learned that that isn't necessarily the case. So n equals 4 supersymmetric Yang-Mills theory contains, is equivalent or dual, or as another description, in terms of a theory of gravity, indeed of strings. So does quantum field theory contain gravity? Depends what you mean by gravity. Yes, it does contain gravity. That gravity might not always be the kind of gravity we're used to when we're talking about gravity, namely long range, weakly coupled, with a good approximation of a classical background. So n equals 4 super Yang-Mills theory contains gravity in that sense in a 5-dimensional space, anti-de Sitter space. QCD contains gravity too, except it's in a very highly curved 5-dimensional, presumably, background with rather strong coupling, and nothing that a classical relativist or a perturbative quantum field theory gravitational physicist would recognize as gravity, but continuously connected to exactly that type of gravity. So quantum field theory, there's another way of putting it, which which maybe this would appeal to you. Even if we had never discovered string theory, which was a remarkable development, a very lucky development coming from strong interactions, enabled us to to develop this part of the framework, field theory, string theory framework, and then to connect them. So it was like a totally separate intellectual development happening in a disconnected region of a space which we now realize is simply connected. Even if that hadn't happened, and we've been sitting around celebrating the triumph of quantum field theory in the Standard Model, we would have realized that we don't really understand quantum field theory because our modern understanding of quantum field theory is based on the Wilsonian viewpoint. And as you, in general, with quantum field theory, move to the ultraviolet, unless you have a theory like QCD, where it becomes trivial in the ultraviolet, we have no understanding of what quantum field theory is. You perturb the theory with irrelevant operators in the infrared, but highly relevant as you go to shorter distances, and there are an infinite number of them. So once you open that Pandora's box, quantum field theory is non-local. There's an infinite number of irrelevant operators, ill-defined. And we could have proceeded along those lines, rather fruitless, because we didn't have this, this other continent, which we finally made contact with, which had successfully completed in the ultraviolet many quantum field theories. Now, that completion contains gravity. The framework of quantum field theory, which is ill-defined and terra incognito in the ultraviolet, is much broader, as you might expect, actually, from the Wilsonian framework, and is not a local, in any sense, a local quantum field theory, as you might expect, because there's no reason why the existence of a finite number of local operators, which is a necessary component for understanding locality in the usual sense, is going to be preserved once you do that. So that's how I view things. We had quantum field theory, didn't really know how to go to the ultraviolet, simple attempts, only introducing a few operators, which is what you do when you try to do perturbative quantum gravity, fail. Had this other outpost there, which looked totally different, and now we realize that it's just part of something, and still we have no idea what the whole picture is.
Is it an urgent question? Well, nothing is urgent. We have 5 minutes left. So, what is your view of
Well, it'll be interesting. We might never find out what the mistake was.
Okay, so let's say